Good afternoon. Welcome to this in the MPL Electronics Reliability webinar series. New low pressure electrical fatigue capability that we're building here at MPL. Acknowledge my colleagues Meenakshy, Ramankutty and Dhaval, Vankhade, who have been responsible for setting up this system and acquiring the data from it. So our objective today is to understand our new electrical fatigue capability. This is something we've developed and validated here at the MPL to understand partial discharge inception voltage and also electrical fatigue testing, which we'll talk about in a little bit more depth in a moment or two. And that's all under low pressure conditions for obviously predominantly aerospace, but also automotive applications have shown interest in this as well. This is a 6-channel system. It's up to 10 kV, up to 20 kV PP on a single channel. We go down to about 5 millibar from ambient, and we can go up to 200 degrees. We haven't gone above ambient at the moment, but we'll be looking to do that in the future. And we're going to talk about our we've looked at electrical fatigue lifetime and how this varies significantly with coating type, test frequency. We haven't seen a correlation in any of the samples so far between PDIV and fatigue lifetime. And the failures do not always occur where the highest field strength in the samples are, and we'll clarify that later. So if you have any technical issues, you can email events@mpl.co.uk. They may be able to help you. Obviously, there's nothing I can do while the webinar's on. During this webinar, your microphones, webcams, and the ability to share will be disabled. If you have any questions, and I hope you will, please submit them through the question and answer here in the bar at the top of your window. And if you want to change your device settings, you can do that by the 3 dots. And if you want captions, they should be able to be naturally generated. They're automatically generated, so as this is a technical webinar, they may not be entirely correct, but the system does its best. So I won't spend too much time talking about high voltage challenges. We're in a world that's increasingly electrified, particularly for e-mobility applications, for vehicles, for more electric aircraft. And if you go up if you go up in voltage, then there is a point at which the insulation between your electrodes will fail, and an electric spark will occur through it. That breakdown voltage depends on the pressure of the gas and the distance between the electrodes, and that relationship is described by Paschen's law or Paschen's curve. And at very low pressures, the voltage needed to break down actually decreases to a minima and then increases again as the pressure goes down. We don't know where we are on this curve, if we're honest at the moment. We know we haven't reached the minima yet when we're down to about 100 millibar in pressure at the moment. So we're on this part of the curve in the sort of ambient to 100 millibar range. The breakdown voltages through air are typically about 3 kV per millimeter at ambient. If you add some plastic insulation over that, you can probably push it to 10 to 30 kilovolts per millimeter. And if you want to go to ceramic, which is obviously non-preferred in e-mobility lightweight applications, you can push that a little bit higher. The phenomena that we are investigating is not that full discharge. It's not an effect known as partial discharge, which occurs in insulation materials where you have a defect in that insulation. So if this is a conformal coating or a potting compound or the dielectric within the layers of a PCB, where you have a defect in that insulation, which you will get, where the voltage across that defect reaches such a point that because it's a low dielectric performance material in a high dielectric performance matrix, you will see a small spark occur across that gap in the insulation. These could be cracks, air bubbles, voids, contamination inside. It's usually an area where, as I say, the dielectric performance is less than the surrounding matrix. And when you where you have that problem, you can see these spikes occurring. These are signals on the ground line, and you can see that there's a discharge occurring, these tall spikes here, across that defect. It's a localized breakdown occurring somewhere inside this insulation, and it's a relatively small discharge. So, okay, potentially annoying, potentially noisy. Our problem occurs when, well, I'll deal with that in a minute. The problem occurs when you get repeated repeated partial discharges. This graph to show how the inception voltage for that partial discharge is occurring. So the inception voltage is, as you increase the voltage across your electrodes, at some point you will see PD on the system. So at some point you will start to see these spikes occurring, usually at the high dB/dt, so that's where your voltage with respect to time is at its highest rate of change. So this in a square waveform you can see occurs at the upper part of the rise time and down part of the rise time. And you can see that typically that can very easily go down towards 50%. With this is a twisted wire pair. This is an acrylic conformal coating on the surface, and you can see, if we look at this acrylic coating, because this is the sort of thing we'll come back to in a bit more depth in a moment, you can see that at ambient pressure, 1000 millibar, we're up around 6-7 kV, and when we get down to 200 millibar in this case, we can see it's around at 3.5. So we've seen a 50% reduction in the inception of the voltage at which this PD occurs as we go to low pressure. And these pressures of 200 millibar are typically the sorts of pressures that are commercial aviation heights. So they're talking at sort of 10,000 meters, 30,000+ feet. Above the automotive, but you can see at 500, that's typical automotive upper end. You can see at 500 millibar, it's already gone down quite significantly from what it would do at sea level. We're told that automotive are interested in increasing this even further. Maybe that's just understanding where the cliff edge is, but that's fine. Now, moving back to what's the problem with partial discharge? It's noisy. The problem is that it starts to degrade the dielectric withstanding voltage of your system. So if you apply continuously partial discharges across the system, when initially, this is for a twisted wire pair, in this case, you can see that we're up at the dielectric withstanding voltage is getting close to 10,000 volts for these two twisted wire pairs that have a coating on the outside of them, probably a polyamide coating in this case. But as we apply PD across these between these two wires, and you start to see the dielectric withstanding voltage drop, and it drops down so that after, in this case, we've aged it for 8 years, it's down almost at 50% of a little bit above 50% of what the voltage is. So it's around about 6.5 kV here. You increase aging for longer until you get down to the point where, in this case, we're below 2000 volts after plus 12 hours of aging. Obviously, the aging time depends on the voltage. It depends on the waveform. It depends on the pressure. But effectively, all of this is happening, and you're getting to the lowering the dielectric withstanding voltage until you're down to the voltage that you're operating at, in which case you get a full electric discharge at that time. So this is what our system is designed to look at. So we have a 6-channel system here, connected to a function generator and a high voltage amplifier, which then goes into a custom-made 6-channel switching box. So we apply about the voltage 6 times in parallel across our sample here. That's inside a vacuum chamber, low pressure chamber, that we can take down to typically 100 millibar. We can go lower, but we tend to stop there just to improve our test times. And if we want, we can go up in temperature as well, but we haven't done a lot of that yet. Just a word about waveforms. We generally apply a bipolar square waveform, and the figures we will quote to you today will always be voltage peak to peak. So they are between the top and bottom ends of the square waveform. So it's a bipolar square waveform, as I said. So, you know, a typical 7K VPP means that we're going to plus 5.5 volts, minus 5.5. Or in this case, 10 VPP is going to plus 5 and minus 5. So if you're just using a positive square waveform, it doesn't necessarily correspond that the PDIV will be at the same level, but that it's not far off of what you'd see with a bipolar waveform anyway. This is a system check on our open channel. As you see, we can generate PD even within our system. So we have to be very careful about the upper voltages that we're driving these things and making sure that the PD that we see is very much a case of PD across a sample and not PD across our system. But and we're looking to improve this constantly all the time, but it is hard work. And you can see here that the PD on the system at 200 millibar is above 7 kV and it's above 5 kV at 100 millibar. These are the sorts of test samples we're working on. These are just effectively single-sided PCBs with tracks in. We connect to the ground level, ground here and here, and then we apply our bipolar square waveform across these connectors here, and so across these curved tracks. The idea of the original design of these curved tracks was so that we were concentrating the field into where the strongest between the center of the curved tracks here. As you can see, that's not quite turned out as we expected it to, but well, this is where we started. We've latterly been looking at longer tracks, and what we tend to see here is that there's more opportunity for partial discharge to occur. So the inception voltage is quite often lower with these sorts of tracks than it is with these curved track systems. So this shows the inception voltage of a coating. We won't refer to specific coating types here or manufacturers, etc., to protect the innocent and the guilty, but this is a typical coating used in the electronics industry. It's a 50 micron thickness, and here we're just looking at the inception voltage at both 50 hertz and 1 kilohertz. We like to try and run the tests as quickly as possible. However, you can form a corona above the surface of the plastic more easily at a higher frequency. So sometimes we have to test down at 50 hertz, which obviously takes us longer to do than it does at 1 kilohertz. However, the inception voltages are not dissimilar, but potentially the failure mode in the coating is, because if you're forming a corona above the plastic, then you may well be damaging the plastic more rapidly than you might do otherwise. Quite often you'll see these red lines appearing on the graph. That means that we could not detect PD on our maximum voltage, which at ambient is up towards 10 kV. So we couldn't see with these samples partial discharges at that voltage. But if we come down here at 100 millibar, you can see that we are down at 4 kVpp and below. So our system is essentially quite simple, but it's much more difficult to achieve this in practice. We apply a fixed voltage to all the channels for a period of what we call the conditioning phase. So we apply that voltage across those 6 samples simultaneously for generally 5 minutes. Some of this data is for a 10-minute conditioning phase. And then at the end of 10 minutes, 5 minutes mostly, we will check that each channel is still isolated, and we'll do that at a low voltage. And if it's failed, we will switch out that channel and just continue to condition the remaining channels that are still in the system. So we run this system until all 6 channels have failed normally. So this shows some data from a simple twisted wire pair. We're testing at 200 millibar. We've got a fixed voltage in this case of 2.5 kVpp. and it's a 1 kilohertz bipolar square waveform. There's 2 wire thicknesses here. These are coated wires, and they're twisted together so that they're in close proximity to each other. You can see that typically at ambient, the inception voltage, we're seeing PD at 1.6 kVp. And when we drop down to 200 millibar, we're seeing much lower voltage. These two are the same, almost certainly because although the wires are different thicknesses, the coatings are very similar. And then we run that at in this case, 2.5 kVp. So we're above the inception voltage, and it will fail within 75 minutes when we are at 2.5 kVp when the PDIV is 1.6. So that's about 13 to 15 trip cycles. This shows similar data for a coating. Again, a PCB conformal coating, coating B in this case. We're testing at 1 kilohertz, bipolar square waveform. This is a 50 micron thick coating. We're testing at 200 millibar now and at 1 kilohertz. And we've got a fixed voltage of 4.7 kVp. Kilovolts peak to peak. What's interesting to note here is that initially the inception voltage of some of these samples is above the electrical fatigue voltage. However, those samples still fail. Sometimes they tend to be longer in terms of failing, but even though there's no PD across these samples, they still fail eventually when we put this signal across them. We're going to start shortly. We don't measure the inception voltage as we go through the test at the moment, but we're going to start doing that soon to see how this inception voltage changes with pressure. But you can see here that we end up with a series of cycle failures, a total time to failure for each of these patterns. And at 1 kilohertz, 4 kV, 200 millibar, we're failing in somewhere in the region of 20 minutes to 500 minutes. And there's obviously a distribution here because we're primarily looking at defects within the coating, and all the defects are not exactly the same across all these samples. So each sample differs slightly from the next. That's why we get a distribution in failures. These show the samples after the failures have occurred. So the thing to bear in mind here is that potentially these samples have failed for 5 minutes. It's somewhere between 0 minutes and 5 minutes since the last time their integrity was checked. So you can see some of these have received a number of full discharges across the system. So one might assume that some of these systems have failed halfway or less than halfway through our conditioning cycle, and therefore they receive lots of failures. Others have just started to fail at the end of their conditioning cycle, so they are in a better condition. But you can see here a wide variety of types of failures. They don't always occur in the area of greatest field strength. That's the other thing to bear in mind. So there's almost certainly something associated with where the defect is in relation to the voltage that we're applying it. The thing to notice with these systems is that they form quite nice viable plots. Now, a viable plot is where we're logging the cumulative failures up the y-axis here, and then logarithmically the time to failure along the bottom. And if all of these samples are failing by the same failure mechanism, they should form a straight line. The gradient of the straight line might tell you something about the failure mechanism. And you can get from this, when you expect potentially your first failure might be if you test a higher number of samples. So here we've got 10 failures. These are basically 2 samples. So the first set of 6 is the circles. The second set of 6 is the second sample. Sorry, it's the squares. And you can see that there is some distribution within this. There's 12 data points here. So we got limited data still at this point, but this is taking us a number of hours to get to this point. But you can see that they, within the 95% percentile confidence range here, we are getting a straight line of these samples, and we're getting a failure time of 0 failure time. You can then decide if you want to take a 50% failure or a 90% failure time, depending on how you want to use statistics in your modeling. This shows a slightly different plot with the same information on. This is our first set of samples, this is our second set of samples, and as I indicated to you before, our first set of samples, the inception voltage was pretty much all above the applied voltage, the electrical fatigue applied voltage, yet they still failed. So this one failed at 500, this one at 250, this one at 275, etc. So this is plotting, as I said, the time to failure against the inception voltage. So even though we've got no PD at the start of this test, we're still failing these as we go along. Second sample, there's a different distribution of inception voltage, a different distribution of defects within the samples, even though it's the same coating. And you can see here that they're broadly spread either side of the inception voltage, but we're still either side of the electrical fatigue voltage, sorry, but we're still seeing these samples above that voltage, they're still failing. This is the same sample, same coating done at 50 Hertz. So now you can see the number of cycles required to fail has gone up, but of course now we're a 50 Hertz bipolar square instead of a 1 kilohertz. So we're applying in every cycle 20 less cycles, so 20 less partial discharges. So you might expect these total times to be 20 times what the first system was. In this case, actually, we've got a slightly thicker coating at 80 microns and the same bipolar square. You can see here that in this case, we've got a parallel tracks as well as curved tracks, although there's the same gap between them. And you can see that again, particularly in the curved tracks, we're not seeing failures at the highest voltage, and we're not seeing failures in the parallel tracks in the same position on the tracks all the time. Again, you can plot that, and in this case, things get slightly more convoluted in that the circles are the first sample, the squares are the second sample, and where we see a bar through the middle, we are that's the parallel tracks, and the non-bars are the curved tracks. So these are all curved tracks up here. One of them hasn't failed or is above the 90% percentile here. And you can see, generally speaking, that we do see much earlier failures in both sets of parallel tracks than we do in curved tracks. So that's indicating to us that the opportunity for PD to occur is greater when you have a parallel track, because the voltage, the field strength across that gap is over a larger section of coating, and therefore more likely to find defects in the coating and more likely to fail. Again, here we've plotted the same. In this case, all our samples, the inception voltage was below the applied voltage, causing failure. This is a different coating. This is coating C. We're with this coating working at 50 Hertz because we were concerned that at a kilohertz we were creating a corona discharge across the surface, which would give us early failures. You can see here, excuse me a moment. This is a 35 micron thick coating. Everything else is the same, 200 millibar, 50 kilohertz, 4K VPP, and a 5-minute cycle time. And again, you can see these failures occurring. Again, some of these, 5.1, the inception voltage is above 4.2, not much, but one at least is above the electrical fatigue voltage. Again, this is a test vehicle with just curved tracks on, but you can see that the failures again are occurring at areas in potentially where the field strength isn't the highest. This shows the Weibull plot. In this case, so the first set of samples, we're seeing the voltage tends to be lower than the second set, but they're all, potentially there's two sets here. There's a I can't remember this one. No, it doesn't. Potentially there's a set of data here that all occur on a straight line, and then there's two outliers here, but they all fall within the 95 percentile line. So we've just shown them as a single line here, but if you're going into this in a bit more depth, you might break these into two populations. But you can see here that generally speaking, well, they do overlap, but mostly the second sample doesn't behave as well as the first sample does. And again, we can see here all of them mostly below the inception voltage, but there was one above and it still failed, and it wasn't actually the one that lasted the longest either. So if you start to plot these systems on the same graph, what we've done now in order to do that and to compare frequencies and coatings is to look at switching operations as opposed to time to failure. So this looks at the number, the time to failure times the frequency. So if it's 1 out, if it's 100 seconds at 50 hertz, then it's obviously 5,000 switching operations. If it's at same at a kilohertz, then it's obviously 100,000 switching operations. So if we plot that switching operations, you can see that there probably isn't much difference, certainly with this coating B, between the 50 hertz and the 1 kilohertz. But there's still, enough to suggest to us here that the 1 kilohertz is failing earlier than the 50 hertz. This may be because there's some corona discharge happening in this sample, which is damaging the plastic coating more readily than it does in the 50 hertz. But you can also see differentiation between these samples. Again, there's an outlier here. If we didn't have this outlier, this line might be a bit more vertical, and in which case there will be a remarkable similarity between the slopes in these lines. The slopes tend to tell you something about the failure mechanism that's happening here. So potentially, even though these coating materials are different chemistries, there's the blood potential here to see that they are failing in a similar manner. Now, this is another coating. It's a 25 micron coating, different chemistry again. Again, testing by the same parameters, 4 kV at 200 millibar, 50 hertz, 5-minute cycle time. One of these hasn't failed. We ran it to 700 plus cycles before we stopped, but we have got sort of 11 out of 12 cycles here. But the other thing to note here is that it's not the sample with the highest inception voltage which has lasted the longest. There are samples here with much higher inception voltages, and they've failed. So, and even within this sample, there are another track here with a higher inception voltage which hasn't gone to the full test time like this sample is. So it's very difficult to see any correlation between inception voltage and failure time. Again, similar sorts of failures depending on how soon before. We are putting these halos down to delamination of the coating from the surface. So there's something happening potentially in terms of adhesion of the coating whilst we're going through this electrical fatigue test. But again, you can see that it's not always the areas of highest field strength where we see the failures. It tends to be, it tends to start at the edges, and that's not too surprising when you look at coatings. Generally, their weak link is the edges where they go around corners, and then it tends to perhaps get from one break through one side, and then it looks for the weakest link on the opposite side, and then starts to flash over between those two failure points. That's our hypothesis at the moment. Same sorts of system for the other sorts of failures. This is a sample that didn't fail. You can still see that haloing occurring in that sample. So perhaps if we'd left it longer, that would still fail as well. The thing about this sample, this coating, two different PCBs again, is that there's quite definitely two populations here. I think I haven't highlighted those, sorry, I thought I had. You can see this population here on the second board is giving us a much more acute angle in the line. It's moving outside the 95% confidence levels here, so we're not quite so keen on the result of this line, but you can see that if you wanted to draw two lines, you could probably draw one through the circles for the first sample and one further to the right, better failure time with the second sample. We're honest, we don't know why these two samples appear differently. We dry the samples out before we start. We try and keep everything as close together, but that'll be an issue that we're looking to gain more information on as we go forward in this project. Most of these samples were below the electrical fatigue applied voltage, so you can see they're failing, and you can definitely see from the lengths of the bars here that the second sample lasted longer than the first sample, even though the inception voltages were generally lower with the second sample than the first sample. And again, plotting all of those on the same graph, you can see potentially here this coating D has got a different slope to the line. All of these three are different chemistries, but you can see that we'll be able to differentiate between these coatings. Thickness might be playing an issue, frequency might be playing an issue. All of these are up for further work to understand as we're going forward. So just in conclusion, we've developed this system that is able to look at the high voltage performance of dielectric materials at low pressure. Our system is test vehicle agnostic. So we can, we have 6 cables coming out from the signal side and 1 signal coming out from the ground line, which is common. We measure the PD on the ground line. We can switch through each individual circuit, measure its inception voltage. We can apply voltage across 6 samples. We can test each sample to see if it's still got integrity or not. But what that sample is, we've chosen to work with PCBs and coatings at the moment. We'll be looking at other samples going forward, but we can plug anything into the end of these samples. We don't really see any correlation at the moment between the inception voltage and this electrical fatigue life. And failures, as we said before, probably ad nauseum, don't necessarily occur where the field strength is at its highest, not always in that narrowest gap between our electrodes. So this system's up and running now. We're continuously running samples through it at pressures down to 100 millibar at the moment. We can go lower. We are limited in the upper voltage at the lower pressures because we start to form corona discharges in air at low pressure. So we have to watch that. But the system is, as I said, device agnostic, so we can plug anything on the end of these systems. Our future plans at the moment, subject to consultation with our partners, and if you'd like to be involved in this project, please drop me an email. I think I've probably forgotten to put my emails on my slides, or maybe it's one at the end anyway, but I'm sure you can Google me at MPL and get that if you need. We'll start soon to look at multi-layer PCBs and understand if we're running tracks or the ground lines and the signal lines on different layers, what the performance of the dielectric between those layers is. We've also got an ongoing project at the moment where we're trying to use optical inspection techniques and filtering of images, particularly where we have a UV fluorescer in the coating, to see if we can identify in advance of where the failures occur, where the failures like to do. So looking at an optical inspection technique to understand quality of coatings, particularly in this electrical fatigue scenario. Our 3D test vehicle is coming online now. So everything we've done so far, we're terming 2D, even though, we have copper tracks in there that have Z-axis heights. we are looking at a partial discharge test vehicle that's got components on the surface. So we're coating those components and seeing if that affects our electrical fatigue performance and our inception voltages. And then also the other thing we'd like to do in the next 12 months or so is look at aged coatings. We're very good in this industry at testing coatings in the as received condition. We're not generally quite so good at testing them in the age condition. So we're looking to take some of these coatings, put them through thermal cycling, which is the commonest aging process. If other people have suggestions of how we might age these coatings, we can do that, and then do our inception voltage and our electrical fatigue testing on the age samples as well, and seeing whether we get a different performance from the age coating than we do the virgin coating. Just a shout out to the next webinar, which will be on the 2nd of June. We've been involved in a DSIP project funded to look at reliability of MOSFETs, silicon power MOSFETs. We've been working here with Swansea University, Vishay and Gen 3 to develop HTRB test systems, as high temperature reverse bias test systems, which are looking to apply a reverse bias across the gate and the MOSFETs, which is a common reliability test for silicon lower voltage, but is it suitable for high voltage? So we've been working on that, and we'll be doing a joint webinar with Swansea and our colleagues at Swansea on the 2nd of June. There's a link at the bottom there, but if you just Google electronic reliability webinars, you should MPL, you should come up with the link to this system to register that one if you have an interest in high voltage testing of MOSFETs. So I think that's me. Again, I must call out my colleagues, Dhaval, Meenakshy, Ling, Anna, Abby, our past colleagues, Merish, Burjo, Adam and Joe, who have all contributed to this project in the past. I shouldn't forget all our industrial partners who we work with, who provide us with coatings, provide us with test samples so we can test out our test methodologies. And hopefully we'll be putting these sorts of tests forward into international standardization in the near future for high voltage dielectric materials.